Okay, before going into main lecture, and the main lecture is again, it's from chapter 17 of your R.C. Hibbeler book, and the title is Planar Kinetics of Rigid Body. And since we are studying the kinetics of rigid bodies, definitely the effect of force, which will be in form of acceleration, will be involved in this chapter. Okay, so let's have a look at mass moment of inertia. So it is a very quick recap for you people. So I will go through few slides, and then remaining for your interest, you can go through this whole lecture. But since it will be involved in coming lecture, that's why I am giving you a slight revision. Okay, what's the objective? Once the first one is to know the moment of inertia of a body, and then what is parallel axis theorem, and then what is radius of gyration. So if you recall these three things, then it will be easy for you to apply these things in the next lecture or in the coming slides or in the coming topics. And what is moment of inertia of composite bodies? So maybe I will not go into much detail regarding this topic, but again, it's very much important. Okay. So what is moment and what is angular acceleration? You are already aware of this thing. So whenever the moment, which is the product of applied force and the moment arm, if it is not zero, definitely then in that case the rigid body experience angular acceleration. It have that angular motion. So in that case, if m is not zero, the rigid body experience angular acceleration, right? And the relationship between m and alpha, that is same as the relationship between f and a. It's similar. It's of similar nature. For example, f is equal to ma. So similar is the relation of m and alpha. F is directly proportional to alpha. Sorry, f is directly proportional to acceleration. In similar way, m is directly proportional to alpha. It's like this, where m is the mass, f is equal to ma in this equation. Like here, m is the mass, and this is the acceleration, linear acceleration. This is the applied force. Now, this moment, this mass m, if we if this mass is larger, then the acceleration produced will be lesser. So this means this is resistance to the applied force, so that it couldn't produce acceleration in this body. Now over here, this is the moment, this is the angular acceleration, and this is the mass moment of inertia. So this basically provides resistance to that angular acceleration in this case. So if mass moment of inertia is higher, this means less angular acceleration will be produced as the result of applied moment. So m is basically mass resistance, whereas, let me remove this thing. I is basically moment of inertia. Okay, so let's not go into details. These are few examples that how to find out mass moment of inertia for various things. Okay, parallel axis theorem, what it says? Um, the moment of inertia about any axis parallel at distance d away from the axis that passes through the center mass is, means for example, if you want to find out the moment of inertia at some other axis that is parallel to the given axis, if you already know moment of inertia about any given axis, and if you want to find out the moment at some other axis, but that other axis, it should be parallel. For example, if you want, if you are having this line, and if you want to find, if you already have moment of inertia at this point, and you want to find out the moment of inertia about some other axis, right? Now this axis is parallel to this one. If you know this distance, this perpendicular distance d, so by using parallel axis theorem, you can find out moment of inertia at this point. So what it says, the moment of inertia about any axis 2 and at a distance d away from the axis passes through the center of mass is, वो कैसे find out होगा? I naught, ठीक है, at any other axis, that is basically equal to ig, that is the initial moment of inertia, plus m d square, that d is basically the perpendicular distance. So again, it's just a recap. That was basically parallel axis theorem. So it will be utilized in our example and in our problem. So Ig is a moment of inertia for mass as center, for mass center G. M is mass of body, and D is basically perpendicular distance between the parallel axis theorem. So, for example, if this is G, this is mass center, we already have moment of inertia at this point, and we want to find it the moment of inertia at some other point, for example, over here or over here. And if this axis, if it is parallel to this one, and if we know this perpendicular distance, so we can use that parallel axis theorem for it. Okay, radius of gyration, again a very important term. Frequently tabulated data related to moment of inertia will be presented in terms of radius of gyration. How to calculate it? So remember these equation, again it will be frequently used. I is equal to mk square, and similarly k is equal to I by m, where k is basically the radius of gyration. I is the moment of inertia, m is basically the mass. So you need to remember these two equations. Okay, I think remaining, just for your own interest, you can go through this slide. I will now shift towards the main class. Okay, so the main topic that we need to cover today, again, it's equation of motion, and in equation of motion or in rigid body kinetics, the first thing that we need to cover, that is basically translation. Okay, but before going into it, let's recall some of our basic concepts from statics. So in statics, for rigid body to be in equilibrium, there was some certain condition. For example, if there are number of forces, this, and this, and also couples or moment acting on an object, and if we say that the object remain in equilibrium, then there must be some condition which should be satisfied. And these conditions are, if you remember, that is summation of all forces acting on this object, that should be equal to 0. And remember, that should include fx is equal to 0, fy should be equal to 0, and if it is 3D problem, if it's 3D case, then fz should be equal to 0. If it is 2D, then this term will be not here. Okay, then the summation of all moment about any arbitrary point, that should be equal to 0. Now this moment, this is basically the moment of forces, the applied forces, plus the externally applied couples. The combination of all these should be equal to 0. So this is basically the first condition, summation of all forces should be equal to 0, and summation of all moment about any point, that should be equal to 0. And this moment, again, it includes the moment due to applied force and the externally applied moment, which, or in other words, the externally applied couple should be equal to 0. The summation of all should be equal to 0. So if these two conditions are satisfied, then the rigid body will be in equilibrium. Okay, so in 2D case, as I have told you, that in case of 3D, we will be have summation of forces along x, y, and z direction should be 0, and then there will be moment about x, moment about y, and moment about z axis should be equal to 0. So if you want to write down this same two conditions in terms of scalar, so you can have six scalar equation for 3D case. But for 2D case, we will be having three equations. These three equations, summation of forces in x direction should be equal to 0, summation of forces in y direction should be equal to 0, and summation of moment about any arbitrary point P, that should also be equal to 0. Again, remember that the total moment, it is the combination of moment due to the applied force as well as the external couples. Summation of all should be equal to 0. If these conditions are satisfied, then the object will remain in state of equilibrium. So this is one of the example of 2D case. This is 2D rigid body equilibrium. Okay. Now, for example, if you are having a rigid body and it is exhibiting planar motion, general planar motion, it is having translation as well as rotation. So in that case, we can draw the free body diagram as I have drawn over here. For example, this is a rigid body, and if you want to draw its free body diagram, So let's say the free body diagram may be like this, as shown over here. Okay, and we already introduced one other diagram which is known as kinetic diagram. So we can also draw the corresponding kinetic diagram for this body, and the kinetic diagram is shown over here. Now in kinetic diagram, what we basically do, we replaces the applied forces with the inertia force. And inertia force is basically the acceleration produced due to the applied force multiplied by the product of rigid body. So in this case, what we have done, the inertia force means this force is having two components, this force is having two components, this is having two components, this is having two components, this have two, and this is having two. Okay, so all forces in x direction, they are producing they are producing some acceleration in the x direction, and the total effect will be the product of mass and the acceleration produced in the x direction. And similarly, the the combination of all forces which are basically producing acceleration in y direction, they can be given as ay multiplied by the mass of that object or rigid body, right? And we assume or in actual the acceleration that is produced along x and along y, it is about that point g. Okay, now to find out the moment about point g, due to this force, this force, this force, this force, as well as the external couple about this point, all of them can be combined as a single moment, right? So in kinetic diagram, what we do, we basically show its effect. And instead of that applied moment, what we basically do, we replace it with inertia couple moment. So in free body diagram, basically we replace the supporting structure and show its effect in terms of forces. Whereas in kinetic diagram, what we basically do, we replace the forces by the inertia force, and we replace the moment by inertia couple moment. So this is basically our kinetic diagram, in which we are having the inertia force and the inertia couple moment instead of the applied moment or couple. Okay. So if you want to write down equations for it, so summation of forces in x direction, that should be equal to acceleration produced at mass center g along x-axis multiplied by the mass of rigid body. Similarly for y-axis, it should be equal to agi multiplied by the mass, and the total moment produced, again it should be equal to the moment produced due to the externally applied force and the external applied couple, and all of them should be equal to this term, right? In this case, it's not equal to 0, it's not statics, it is dynamics. Okay, now what is that mkp? So mkp is basically the moment or the kinetic moment at any random point p. For example, at this point, if you want to find out moment at this point, so maybe the moment at this point may be different, but at any random point, if you want to find out, so that can be written as mk. And what is mk? This has been given the name of kinetic moment about point p. Okay, so again, as I have told you, the question may arise in everyone's mind that what is mkp. So mkp, for example, if this was the point, if this was the point, so definitely this force, it will be having some moment about point p, and which should be this force multiplied by this distance. So this force multiplied by this distance, and this force multiplied by this distance, and this will remain as it is. This one will remain, that inertia couple moment will remain as it is. Okay, so mkp, the kinetic moment about point p, it can be given as this force multiplied by perpendicular distance magxy or dy, this term, and this force multiplied by perpendicular distance, which is dx, it will give us moment due to this force about point p. And remember, this force about point p will produce moment in clockwise direction, so it should be positive. and this one will produce moment about P as sorry, this one as anti-clockwise, and this one will produce as clockwise, and we take clockwise as negative, right? Again, this one is anti-clockwise, so it should be positive. So this is magx dot dy minus magy dot dx, and this is basically the inertia couple moment which we have. It will remain same throughout the body as couple remains same. It doesn't change by the application, the point of application of force or moment. Okay, so over here, what we were doing, we were finding the moment about any arbitrary point P. So if you want to summarize the moment about point G, this one, if we summarize the resultant moment about point G, like on this point, so what will happen? Now the moment due to this force and the moment due to this force, it will become zero, because this force as well as this force, it passes through this point G. So the forces in x direction and the forces in y direction are their effect, which will remain same, whereas the moment about point G, that should be equal to the moment due to applied forces and the couple, that should be equal to Ig alpha. How it should be equal to Ig alpha? Because moment due to this one should be equal to zero, moment due to this one should be equal to zero, and the only moment that will be left, that will be basically the inertia couple moment. So that's why we put that one as Ig alpha. Oh, now let's move forward. If we consider that in general plane motion, instead of general plane motion, if we are having only translation, so in case of translation, the whole body moves from one point to another, and every point on the body, it is having same motion, if we recall it from previous classes. So in this case, we do not have any rotation. If we don't have any rotation, this means that there is no couple, externally applied couple, or we don't have any inertia moment couple in this case, right? So for translation case, uh, let's say this is a free body diagram. If we draw kinetic diagram, and if you want to find out if you are having only translation, right? So in this case, there will be no rotation, means the object will move in a straight line, or it will follow some curve path, but it will not follow, or it will not rotate about some specific axis or point. So this means that Ig in this case, that is equal to zero, right? So if we put this thing in the equation, so summation of forces in x direction, it will remain same, summation of forces in y direction, it will remain same. The moment due to externally applied forces and plus the couple, that should be equal to mkp, right? Which is the kinetic moment about any arbitrary point P. Okay. Now in this case, if you want to find out moment about point P, so moment due to this force, moment due to this force will be zero, and there is no rotation, there will be no moment at all. But if you want to find it out at point P, so at point P, there is no externally applied couple or moment or inertia moment or inertia couple. So this term Ig will be removed. The only moment, if you want to find it out at point P, it will be due to this force and this force, right? So mkp will be due to magx multiplied by the perpendicular distance, which is dy, and magy multiplied by perpendicular distance, which is dx, right? And if remember, over here we don't have any igy, right? In this case, we don't have this ig alpha, not igy, sorry, ig alpha, because it's a pure translation case. Now let's say if I don't want to find out the summation or the total moment about point P, if I want to summarize moment at this point G, then what will be the situation? In that case, the moment due to this force as well as the moment due to this force will be zero. And if it is translation, this means there is no externally applied couple. So this whole term will become 0. So let's consider that case too. Equation of motion for translation, right? And you can see in this case, if you want to find it out at point G and there is no externally applied couple, so in that case, summation of forces in x, it will remain same, summation of forces in y remains same, but the summation of moment about point G or about mass center G, it will be equal to 0, because the moment due to applied forces is 0, and the moment due to external applied moment or external applied couple or inertia couple, it is also equal to 0. Okay, now let's consider an example. The toy cart with this load has mass of 0.2 kg at mass center at G, is being pulled by a horizontal force of magnitude F is equal to 0.8 Newton. This is basically that force. Okay, and the mass is given at 0.2 kg at point G, at this point. Is being pulled by horizontal force. Okay, determine the acceleration of the cart as well as the normal forces on the pair of wheels A and B respectively. Assume the wheels are free to roll and have negligible mass. Okay, so we don't need to consider the mass of wheel, and they say they are free to roll. This means there is no friction involved. Okay, so what we need to do for the first step, we need to find out the free body diagram. Okay, so the free body diagram, weight will act at point G and the normal forces at wheel 1 and at wheel 2, let represented by an A and an B. Okay, if you want to draw the corresponding kinetic diagram, so in kinetic diagram, what we can do, we will replace the force by its inertial effect. So we know that F is equal to ma. The motion is in this direction. So the kinetic diagram, it will be again showing direction towards the left. So at point G, the effect of force or applied force will be replaced, or the applied force will be replaced by MAGX. So this is basically the corresponding kinetic diagram. Now what we need to find out, we need to find out acceleration of cart as well as the normal and the normal forces at both field, means we need to find out an A and an B. So we have those equations, that is summation of forces in x, summation of forces in y, and the summation of moment, all should be equal to 0. So let's apply those one. Summation of forces along x-axis should be equal to max, and definitely it's about point G, so magx, it should be equal to this one. So in x direction we are having just one force, that is 0.8. So put that 0.8, and m is 0.2, and agx will left out. So from here we can find out agx. Okay, then summation of forces in y direction. So in y direction we are having this force, and we are having w. So w is equal to mg. Okay, so na plus nb and this mg. But in this equation now we are having two unknowns, so this equation cannot be solved completely. Okay, so now let's have another equation, that is summation of moment about uh, point G or about any other point. Let's say initially consider it as about point G, about this point. So this force will be having moment about this one, this force will be having moment about this one. When you write down this equation, okay, this force will also have moment about point G, and that should be equal to 0.8 multiplied by this perpendicular distance. How much is this perpendicular distance? This is 100, this is 40, so that should be equal to 60 mm divided by 1000. Okay, and this multiplied by 50, this multiplied by 30, divided by 1000, divided by 1000, and this one will give us this complete equation. Now we are having two equations and two unknowns. Find out the value of an A from here or an B from here and put it over here. We will get an A, and once you get an A, put it over here or over here, you will get an B value, right? So the acceleration was basically in x direction, there was no acceleration in y direction, so this is the acceleration, and these are the required normal values. Okay, we can also do for example, we can find out the moment about any arbitrary point, for example point A or point B, right? So let's see it that way. Summation of moment about point X, it will remain as it is. Summation of moment about Y, it will remain as it is. Okay. And moment about point A, for example, if you want to find out moment about point A, so the moment due to this force, it will be 0. Moment due to this force, 0.8 multiplied by 40 divided by 1000. It is already given, and it is already given. So m multiplied by 9.81 multiplied by this perpendicular distance. So again, it's a numerical value. So the only unknown in this equation will be nb multiplied by 80 divided by 1000. So this nb is only unknown. So from this single equation, we can determine this nb. Put this nb over here in this equation, and we can find out that na value. So it's up to you whether you want to find out the moment about any arbitrary point, or you want to find it out about point G. Okay, now let's look at another example. We have an 80 lb force is applied. This is 80 lb force to 100 lb uniform crate as shown. This is a uniform crate. Uniform crate means that mass center will be at the mid. And if this is 4 feet, so it will be somewhere at 2 feet, and if this is 3, it will be somewhere at 1.5. So mean mass center will be somewhere over here. Okay, 100 lb uniform crate as shown. 100 lb means its weight. Determine the linear acceleration ag of this crate. Means if it's move in this direction, so they are asking for ag. The coefficient of kinetic friction between crate and surface is 0.2. And this is moving, so the coefficient of friction over here, that is 0.2. Okay, what they are asking, determine the linear acceleration. So the first step will be definitely to draw the free body diagram. Okay, so we draw the free body diagram, and definitely at mass center G, the weight will act, which is 100 lb, and definitely the weight is acting downward, so reaction from the surface, which would be normal to the surface, and if it is moving forward in this direction, if it is moving forward in this direction, so reaction force will be opposite. This is basically the reaction force. Okay, now since the object is moving, so this force, the reaction force can be at any point. It can be at here, it can be at here. Okay, let's imagine that we consider this point. Let the normal force and the friction force act at this point, right? Okay, now let's assume that the distance from this central line till this, the point that we select A, is x. Okay, if this x, it becomes equal to 1.5 feet, so this means if it goes over here, or if it is greater than 1.5 feet, so in that case sliding will not occur. I mean, if it is having reaction at this point only, and you are applying this force from here, so what will happen? Instead of sliding, it will tip over. Means this one will tip over like this, right? And sliding will not occur. So this is some random point. We don't know about that x value. We need to find it out. But what we are assuming, that we assume sliding occurs, not tipping, right? So we can find out that friction force. So friction force, it's very much easy. That friction force should be equal to mu k and n. Sorry. Okay, how we can find out n? So let's see it. I mean, let's summation of forces in x direction should be equal to zero. Should be equal to the acceleration produced in x direction multiplied by the mass. So the acceleration is produced only in x direction. Okay, we already have mass, and in fact we don't have mass. We have the weight. So weight divided by g. So weight divided by g, it will give us weight is 100 divided by g value 32.2. So we will get the mass. Okay, and summation of forces in the x direction. So in x direction we have 180 Newton force, and the other one is the frictional force, which is basically 0.2, which is the coefficient of kinetic friction and value. Okay, so let's give this equation as equation A name. Then the summation of forces in y direction. So in y direction, how many forces do we have? we have this force which is acting downward, which is the weight, and normal. So summation of force in y direction. So from here we can get n is equal to 100. Okay, if you put this n over here, so we can get this Ag value, which is over here, right? So the problem is solved. Now over here we have made one assumption: assume sliding, not tipping occurs. So now let's check whether this assumption is okay or not. So we need to find out this x value. We need to find out this x value. So let's use the third equation, which is a moment about point G. The moment about point G, that should be equal to 0. As we are saying that sliding is occurring, not tipping. Uh, so summation of moment about mass center G is equal to 0. Okay, so this is the applied force multiplied by how much is the distance over here. Okay,
Okay.
this is the applied force, and this is 2. The center will be at 2, right?
Yes, sir.
So 2. Okay, and this means this is applied at 3. This is applied at 3. So the distance between this point and this point should be how much? It should be 1, right?
Yes, sir.
Okay, so 80 into 1, and then n multiplied by x, and definitely this force will not be having any moment. Okay, so when you solve it, what you will get the value of x, and x is equal to 1.2 feet, which is less than 1.5 feet. So this means x is equal to 1.2 feet, which is less than the value which I mentioned, 1.5 feet. So this means it will not tip over. Instead, we will be having a sliding effect. Okay, so this was the problem which we just solved. Okay, now let's move towards the other portion of today's class, which is basically again we are deriving the equation of motion, but in this case we are considering rotation about fixed axis. So before this, we consider the equation of motion for pure translation case. And remember, we are studying general planar motion, which is combination of translation and rotation. So we studied translation, and now we are moving towards rotation, and this is rotation about a fixed axis. Okay, so over here, this is a case. This rigid body is pinned at point O. So this means the effect of applied force, what it can do, it can make this object rotate in this direction or in this direction. So what they have shown over here, that the rotation or the angular motion in counterclockwise direction, let it be positive, or let these be positive. This is the angular acceleration and this is the angular velocity, right? So in this case there is no translation, because this link is fixed. This pin, it is a pinpoint, and this object cannot translate in this direction or in this direction or up and down direction. What it can do, it can rotate about this pinpoint. If you want to draw its free body diagram, so in free body diagram, what will happen, instead of that pinpoint, we will show force. Instead of support, we will show the force that it causes, or which basically stop it from moving, or which is basically stopping it from translation. Okay, so the same equation, that is summation of forces in x direction will be applied, summation of forces in y direction will be applied, and the summation of moment about any random point P will be applied. And you know that that is equal to summation of kinetic moment about any random point P. So that random point P can be anywhere. If you want to draw its kinetic diagram, so definitely in kinetic diagram, what we will do, we will basically replace the applied forces with the inertia force, and the applied couple with inertia couple moment. So here is the corresponding kinetic diagram. Okay, now to analyze the pure rotation case, in case of general plane motion, it's very much convenient to use anti-coordinate system rather than the xy coordinate system, because we are having rotation, and at every point the direction changes. So it's very much convenient to use the anti-coordinate system. You are already aware about that anti-coordinate system. because we use it in our curvilinear uh, cases, curvilinear analysis, curvilinear motion analysis. Okay, so let's say if this is the fixed point and that rigid body is rotating like this, so let's consider this path, the rotation path. So at let's consider that mass center G. Okay, and let's define our anti-coordinate system at this point. So definitely the T will be along the tangent, or it will be tangent to the path, or it will be in the tangential direction. So let this axis be called T, and definitely N will be perpendicular to T. So let this be the T. How we can draw that T? So T is definitely tangent to the path. So anywhere tangent to the path, you can select that T axis. Okay, and N will be perpendicular, and remember N is always directed towards the point about which rotation takes place. Okay, so if we draw the corresponding kinetic diagram, again, the inertia forces that will be having components along T, and that will be having component along N, right? And definitely the inertia couple moment, it will remain as it is, Ig alpha. So the summation of moment, summation of forces along x direction. In this case, we don't have the x direction. Instead, we have x. Instead of x and y, we have anti-coordinate system. So summation of forces along n direction, that should be equal to mass and acceleration produced in n direction at point G, and the summation of forces along t direction, that should be equal to the product of acceleration produced at point G along t direction multiplied by the mass of rigid body, and the moment, that is basically the summation of kinetic moment at any arbitrary point A. Okay, so as we know that from our previous lecture, from our previous study, that the acceleration along n axis, which is an, it can be given as omega square r, and the acceleration along t, that is equal to alpha r alpha, whatever you call it. Similarly, it's similar like v is equal to r omega, r v is equal to omega r. So similarly, for acceleration at is equal to alpha r. Okay, and an is basically omega square r. So if you put this an and a t value over here in this equation, so you will get something like this: m omega square rg and m alpha rg, where rg is basically that perpendicular distance. For example, if this is MAGT, this is basically the distance of point G from the point about which rotation takes place. So this is RG, the position vector which is showing the position of point G from the center of rotation. Okay, means for example, if this is the point where rotation takes place and this is the mass center G, so the position vector which is showing position of point G with respect to this origin, or with respect to the point about which rotation takes place, this is the RG. Okay, so in this case, the kinetic moment, which is mk about any random point P, that should be equal to, for example, this is the random point P. The moment due to this force, the moment due to this force MAGT, it should be equal to, it should be multiplied with the perpendicular distance dt, MAGT multiplied by dt, and MAG, and that should be multiplied with this perpendicular distance, which is dn, and the inertia couple moment, it will remain as it is, which is Ig alpha. Okay, if you want, if you want to find out, or summarize moment about point G, in this case, the moment due to this point and moment due to this point, it will be 0. If you want to find it out about point G, so moment due to this point and moment due to this point will be 0, and the only moment it will be due to the externally applied couple. So Fn is equal to m omega square rg, ft as it is, m alpha rg, and mg will be equal to due to that inertia couple moment only, right?
Yes, sir.
Okay. And if let's say, for example, if you want to find out moment about point O, if you want to find out moment about point O, so in this case we are having two components. One is MAGT, one is MAGN. So MAGN is passing through this point O. So due to this one, we don't have any moment. So moment produced due to MAGN, that should be equal to 0. The only moment will be MAGT multiplied by this perpendicular distance, which is RG, right? And definitely this inertia couple moment. So if you want to find out moment about point O, that will be equal to I naught alpha. What is I naught? Let's see it. So M.K about point O kinetic moment, summation of kinetic moment about point A, that should be equal to MAGT, right? And multiply by this RG. So MAGT is basically equal to M alpha RG, M alpha, and that RG, and this is the, let me, you can see it from here, that AT is equal to alpha R. AT is equal to alpha R. So M A G T, that should be equal to M alpha RG, right? And this should be multiplied with the perpendicular distance, which is RG. So that is basically MA alpha RG, and it should be multiplied with the perpendicular distance RG, right? And this is basically the inertial externally applied inertia couple moment, IG alpha. Okay, if we take that alpha carbon from both these equations, so what we will get, mr square g plus ig. So this from parallel axis theorem, if you recall, which we just discussed, that if you know about if you know the moment of inertia about the mass center g, and if you know the perpendicular distance, if you know this perpendicular distance, right? So you can find out the moment of inertia, or you can find out the moment of inertia at any other point. And in this case, the other point is O. So we can find out moment of inertia about point O. So IO, if you want to find out this thing, and if you already know moment of inertia at point G, so how you can do it? This can be M multiplied by the perpendicular distance and its square. We can write this one from the parallel axis theorem. So from parallel axis theorem, we can replace this term by I naught alpha. Okay. Now let's have an example. A 50 kg object with radius of gyration, kg is equal to 0.4. Okay, so the radius of gyration over here is given. About its center of gravity, this is center of gravity, is pinned at point O. This one is pinned here, and subjected to couple moment as shown, which is the, okay, this is the couple moment. If at this instant it has angular velocity of 6 radian per second, the angular velocity is given. Determine the support reaction at point O and its angular acceleration. Okay, angular acceleration means they are asking for alpha and support reaction at this point. Okay, so now let's draw the free body diagram. For the free body diagram, weight will be acting downward, and definitely it will be at point G, and we remove the support. So for when we remove the support, we have to show the reaction force which we had due to that support. Okay, since we are having rotation only, translation is not possible because we are having a pin joint. Okay, So for rotation, we have just discussed that anti-coordinate system will be preferable. Okay, so let's draw our anti-coordinate system. So let's this one be the tangential T, and the normal one will be definitely perpendicular to it, that is N. Okay, so this W, it can have two components. This W now, it can have two components, one along T and one along N. Remember, this 80 degree is already given to us in the in the question. Okay, so what is this 80 degree? This is basically the angle between, this is the angle between horizontal and N, right? And we know that the angle between perpendicular arms remains same. So if I draw a perpendicular, and a perpendicular to horizontal, which perpendicular to horizontal is basically this vertical, and perpendicular to N will be T. So the angle between these two should also be 80 degrees, right? This one should also be equal to 80 degree. Okay, so let's find out that components. So W component along T, that should be equal to W cos 80 degree, and W is 50 multiplied by 9.81. So this is W component 491 cos of 80, and the component along N should be 491, in other words 50 multiplied by 9.81 into sine 80 degree. And definitely this O, again it will be having two components, one along this one along N axis and one along T axis. So let's this one be OT, this one will be ON, and the couple moment that we have externally applied couple, it is 100 Newton meter. So now let's apply our equation. Okay, so it is the same diagram, free body diagram. If you want to draw its a kinetic diagram, so in kinetic diagram, these forces will be represented. These forces will be represented by the corresponding inertial force. So this is the corresponding inertial force, or the acceleration produced along T direction multiplied by the mass of rigid body, the acceleration produced along and multiplied with the mass of rigid body. And definitely instead of simple couple moment, we need to replace it with the inertial couple moment, which is basically equal to Ig alpha. Okay, so now let's apply summation of forces along T direction and summation of forces along N direction. So summation of forces along N direction, that should be equal to M omega square Rg, or in other words, this is basically M Ang, and we know that An is basically equal to omega square Rg, right? So the forces that we have along N, which force do we have along N? 491 sine 80 degree, 491 sine 80 degree, and we have On, and we don't have any other force. So these two forces are equal to M omega square Rg. Okay, now summation of forces in T direction. In T direction, we have 491 cos 80, and this should be with negative sign, and OT with positive. Okay, do we have? No, we don't have any other. This is second equation, and that should be equal to, this one should be equal to M AT, and M AT is again, AT is equal to alpha R. Okay, and we have this value of M, we have this value of M, we have this value of R. What is the value of R from here till this point? This is given in the question. This is 0.6. So when you put it over here, you get this value, 30 alpha. Okay, so now in this case, in this equation, alpha is unknown. Alpha is unknown. Okay, over here On is unknown, and over here OT is unknown. So it's very difficult situation. It's not possible to solve it with just these two equations. So maybe uh, do we have omega value? Oh, right, omega is given over here. Omega is given. The value of omega is given over here, which is 6 radian per second. So if we put that omega over here, we already have mass, we already have Rg. So from here we can find out On. So this is basically On. Okay, from this equation, in this equation, just we are having two unknown. One is that OT and the other one is alpha. We already have On. If you find out OT, so the reaction force will be determined. And we also need alpha. This is also asked in the question. So let's try to find out moment about any point. Let's try to find it out moment about point O. Now moment about point O due to this force, it will be zero. It will be zero. And moment due to this force MAGT multiplied by 0.6, that will be basically the moment and definitely the externally applied moment. So the externally applied moment, it is 100, or in other words, the externally applied couple. Okay, and it is in counterclockwise, so let it be positive. Okay, about point O. And then we have this MAGT. MAGT. This is mass multiplied by Ag, and definitely AGT is equal to alpha Rg. Okay, multiply by that 0.6. Okay, and this one should be 491 cos 80 degree. Okay, if you look at this one, the direction of this force, it is opposite to t. So this is causing moment in clockwise direction. This one is causing moment in clockwise direction. So this should be equal to minus. So 491 cos of 80 degree, right? And that should be equal to the acceleration produced along t direction multiplied by the mass, right? And that is equal to 30 alpha. Oh, sorry, I went to the wrong equation now. Here, this was basically the 100 Newton meter, and then this force 491 cos of 80, 491 cos of 80. This is basically the force that we have over here, and this should be multiplied with this one, with this distance. So 491 cos of 80 multiplied by 0.6, right? And that should be equal to I naught alpha. I naught alpha y from this equation, from this one. For pure rotation, we are having these three equations. One is this one is this one, and one is this one. Fn, Ft, and M naught. This is Fn, that is equal to M omega square Rg, Ft, that is equal to M alpha Rg, and M about point O, that is equal to I naught alpha, right? So when we put values in this equation, what we get On value. When we put values in this equation, we got two unknown, OT and alpha. So then we use that summation of moment about point O. So one moment is 100 Newton meter. The moment due to this force about point O is 0. And the moment due to this force, that is basically this force multiplied by 0.6, right? And that is equal to I naught alpha. Okay. And we know that I naught is equal to Ig plus mr square g alpha, right? And we already know from radius of gyration formula, if you go through it, we can write Ig is equal to mkg square plus mrg square. This is basically Ig from radius of gyration formula. Okay, that is mrg square, alpha is as it is. And on the other hand, when you put this value, m value, kg value, m value, rg value in this equation, when you put this value, 50 is basically m. And over here we have that alpha. On the right side, what we have, we basically have 26 alpha, not 26 alpha, this one. Okay, when you solve it, this one alpha. So when you solve this one, this basically comes out 26, and this is alpha. Okay, so now this term, this left hand term is equal to 26 alpha. So when you solve it, you get alpha is equal to 1.88 radian per second. So let me clear the screen. Okay, now let's. Okay, so we were having three equations. Let me show it to you again. These three equations. This one, and this one. Summation of forces in n direction. So n direction we were having this force and this force only. This one and this one, and that was equal to m omega square rg. We have m, we have omega, we have rg. When you put the value, we get on. Then summation of forces along t, that is equal to m alpha rg. We have m, we have rg, so that got 30 alpha. So we have that we don't have ot, we don't have alpha, and that will remain as it is. So OT and the other force in x direction 491 cos 80 degree. Okay. Then third equation, that was moment about point O. So moment about point O due to this force should be equal to 0 because this force passes through point O, and moment due to this force, that should be 491 cos 80 multiplied by 0.6. 491 cos 80 multiplied by 0.6, and that should be equal to I naught alpha. I naught is basically equal to Ig plus mr square g from parallel axis theorem. Okay, from radius of gyration, we can put Ig equal to m.K square g, and mr square g will remain as it is. We take m common, which and its value is 50. So let's write it 50. Kg is 0.4, Rg is 0.6, right? Alpha will be as it is. When you solve it, you will get 26 alpha. So 26 alpha, that is equal to 100 minus 491 cos 80 multiplied by 0.6. When you solve it, what you will get? You will get the value of alpha. So now, when you get that alpha value, put it over here in this equation. When you put it over here, what you will get? You will get the value of OT. So now we get ON, we get OT. If you want to find out OT square plus ON square. Okay, and this is basically the required answer. Okay. What they are doing basically, alternatively, if they are asking if you want to find out moment at some other point, not at point O, so you can also do it. Means you can find out moment at point G. So in this case, the moment due to the light forces, that is 491 cos 18, 491 sin 80, that will be 0, and the only moment that will be basically the externally applied moment, right? In this case, so you can go through this one also. Okay, so the suggested problems for these topics, they are basically um, since we are doing chapter 17, so you can go through example 17.5, 17.6, 17.7, and then for the next topic 17.9 to 17.12, and you also need to go through the related problem from the same book. Okay, so this is basically the end of class. Now the topics that we need to cover, or that's left, is basically the equation of motion, and specifically the general plane motion, in which we have a combination of rotation and translation. And then we have chapter 18, that is planar kinetics of rigid body, and in which we basically study the work and energy. And finally, the impulse and momentum of rigid body. So these are the topics uh, left which we didn't cover yet. Okay, if you have any question regarding today's class, you can ask. Otherwise, I will put the recording off.